Hello everyone, welcome to Statistical Foundation for Big Data Analysis. We shall start our 11th module today. This is going to be a module on random graphs, and random graphs will form a very key component in studying structured network data. Now remember, at the beginning we talked about structured and unstructured data, and I said like often the variables, like if you view the data as a vector of values of various features, the features may have certain relation between them, and it's maybe important to not just understand the values of each features, but the relations between them as part of the data point itself. Just to give you an example, I mean we discussed this in our first module, I think lecture 4 or 5 in our first module, when we were discussing graph data. I actually recall this. I discussed this example of friendship net, Facebook data and friendship data, adjacency matrix data, etc. So, but just to quickly recall, if you are not mathematically, just in simple terms, if you are really trying to analyze various Facebook profiles, it merely not enough to, let us say, just assign a particular value to each profile and take the totality, or it's, I mean, let us say you want to assign a value that like how many people visit that profile on an average, or how many followers that profile has. Those values in themselves need not be just enough to capture the truth or the information about a particular profile. For example, if you are, for example, you are interested in discussing the fan behavior of various football clubs, if you go to the Facebook pages of each football club, they have many followers. To understand the difference between various football clubs, fan behavior or the commercial behavior of each football club, you may actually need to understand how the fans of a club interact with each other. So, if you keep that football club profile at the center, you look at all the fans that follows that profile, the connectivity structure amongst the fans, like how many of them are friends of each other, how densely that network is connected, like how many, like if a club A has 100 fans, F1, F2, F100, how many pairs amongst these Fijs are actually friends with each other may give you that number, the total number, how many of these 100 choose 2 pairs are actually friends to each other, gives you key information about how the club's social community behaves, and that will differ from club to club. So, when you are comparing club data, football club data, this totality of this whole friends, all the profiles that are followers of that club profile, this totality actually gives you one data point for that club. This in turn leads us to network data, where each data point is actually a network. I mean, the whole data point may come as a giant network, and each data point may be node and surrounding some few nodes surrounding that particular node. It can manifest it in various different ways, but the key idea here is that the features are various nodes, and also the relations between various nodes are also features. Basically, you are interested in values of each nodes and the relation between nodes. This leads us to network data. We will formally see what consists of a network data and how one does inference in this module itself. We will do it in largely abstract random graphs setting in this module. Well, graph setting, and because we are in a statistical scenario, there will be certain probability or randomness involved. So, that will get into random graph. Basically, graph is the mathematical structure underlying the network, and because there will be probability involved, because we are in a data analysis context, we will get into something called random graph. I mean, we will see the formal definition, etc. in a moment, but like the network data, just to give you examples, the practical examples of network data. Facebook friendship network, of course, is one key example. Same for Twitter following network, Instagram interaction network. These are key social media networks, social network examples. Apart from social network, which is perhaps most of you use, there are very important network data in biology: protein-protein interaction network, gene regulatory network, and neural connectivity network. These are examples of biologic networks that are coming from biology. They are becoming so important that a new area called network medicine is emerging that tries to find new drugs by analyzing bionetworks. So what happened is, so just to give you a very, I cannot resist giving you a quick glimpse what happens there. Now suppose a disease network is something like a certain portion of your immunological network got affected by some disease. The disease network looks something like some graph. Various medication, what it does, it tries to attack some of these disease molecules. One guess will be the medication which affects or alters the graph maximum may be the most effective network. Now you do this analysis, like removal of which molecules in the network affects the graph maximum, but does not harm it too much, harm the broader immunological system too much. If you can find those few molecules, like just removal of them will affect the graph, that is cure the disease, but keep the original immune system intact, becomes your target molecules for pharmaceutical research. You try to come up with medication which can remove just those molecules without affecting the others. So you can only do this by studying the structure of this underlying graph of this biological network. So this is what network medicine does. So another example of course will be the communication network, the email exchange networks which all the email servers preserve, phone call networks, internet routing network which is basically used all the time by the telecommunication companies. Other interesting examples of networks are technological networks which are power grid network, transportation network, road networks, sensor network. There are information networks like web hyperlink network, like every, if you view various websites as nodes, there are connections between them by if the hyperlink for the another website is present in this website. Citation network, if you consider various research papers as each nodes, if one research paper refers to other research paper, there a link gets connected. Economic networks, of course, this is one of perhaps the ancient example of network. Trade networks between different communities. Actually controlling supply chain network is one of the biggest focus of big powers. Internet banking, interbanking lending networks. So for various banks, you can kind of, one bank can lend from another. If you have guarantee from one bank, you can get money from some other bank and so on. There was one time, there was I read this incident from in a book, like there was a big banker in Bengal, like in Murshidabad, called Sheths, Jagat Sheths, and his stamp had such a strong guarantee that even people in Central Asia, Amirs in Bukhara, etc., will lend money if you had him as a guarantee. So this network of various bankings, it's an ancient system, and this is still prevalent as a network example of network data. So this is an example of airline network. So various nodes are your various airports, and two nodes are joined if there is a direct airline between them. Just look how huge and complicated this is. Because after all, a course for statistics where big data is potentially relevant. Look at the size of this network, and this is growing every day, changing every day. There are hundreds of airline companies, there are thousands of planes following. If you want to actually analyze the network data, it will grow exponentially if you are focusing one node, 5 node at a time, 3 node at a time, various combination of nodes at a time. This will give you a gigantic network data set. This is another example. So, this is the network of British Airways airline network. This is Emirates network, this is Turkish Airlines network, and this is Deutsche Lufthansa network. You can see that they have 2 hubs. If you enlarge the picture a bit, you can see 2 hubs. I have kept the link for these pictures here. The Emirates have 1 hub, Lufthansa has 2 hubs, and Turkish also has 1 hub. So, all these are examples of networks. So, the data corresponding to these networks will look like, ideally for each of these airline, which is basically each of these network, if you vectorize this, may look like, for example, for British Airways, this million passengers with this percentage of the whole thing, this many nodes, this many links. So, for British Airways, it has the 33.276% of the passengers, 183 nodes, 405 links. These together with some other parameters will form the totality of the British Airways data. But these numerical values, if you compare these numerical values, these million passengers, this many nodes, this many links, this density, this is still a part of this whole totality, where this picture is also another significant part. Neither these values nor just these blanket pictures can perhaps substitute for the other. This gives you one view. You just visually, if you just visually look at British Airways versus, let us say, Turkish airline, or British Airways versus Emirates, clearly see there is a difference, visual difference between these graphs. That thing itself, for example, Emirates has just 1 hub, British Airways has 2 hubs. Those informations, the structural informations, are as important in case of network data as these numerical values. So, with this background and just recalling of what I think, whatever I just quickly recalled, I essentially mentioned some of this in first week also. I will get into the mathematical structure underlying networks, namely graphs. Graphs forms the mathematical backbone of networks. Just like vectors and matrices forms the backbone of multivariate classical multivariate statistical data, graphs forms backbone of network data. So, graph G is an ordered pair. It is a set of, you have a set of points and lines joining them. The set of points is called the vertices or nodes, and the lines joining them are called edges or links. For now, we are taking for this course. So, graphs can be many things. These links can have directions, they can have weights, there can be many other things, but for now we are defining the most basic structure, where links are just lines joining them. So, this is one example of a graph. There are 3 nodes, 1, 2, 3, that is 3 vertices, and there are 1 and 2 are joined, 2 and 3 are joined. For example, 1 and 3 is not joined. This is, for example, not there. This is not there, not an edge, and these are edges. So, you have bunch of points, some of them can be joined, some of them need not be joined. That gives you a graph structure. Simple enough, and we will see that this simple structure itself gives a fairly robust foundation for network. So, just to give you another example, vertex set is basically the collection of nodes. Just give you some of the basics, not examples, some of the terminologies. The vertex set is essentially those nodes, and the edge set is the collection of the pairs which are actually joined by link or some line or some edge. So, here it is another example where the vertices are A, B, C, D, and edges are A, B, B, C, C, D, and A, D. This is basically a cycle. A graph is called bipartite if it can be partitioned into 2 sets of nodes, V1 and V2, disjoint, such that all edges are from one vertex in V1 to another vertex in V2. Often what happens is that, like So bipartite graphs have many applications, many practical applications. One interesting use of bipartite graph is to bipartite graphs capture directions. Why we are interested? There are many motivations, but just to give you one use of it is to capture direction. So, one for example, if your networks, instead your graph actually has direction 1, 2, 4, 5. So, it is a, let us say it is a follower network. We are interested in following. If you take bunch of Facebook book profiles and you are interested in the following structure, follower structure. A follows B need not mean B follows A, and we at some point for some analysis this direction may be important. So, suppose here 1 follows 2, 2 follows 4, 2 follows 5, 5 follows 3 and 1 follows 3. Suppose this is your structure, but the way we formally defined, we defined edges to be just pairs. We defined vertices to be just points, edges to be pairs. There is no way to capture these directions. So, what we do, we duplicate the vertices, we create a new bipartite. To capture this, we create a bipartite graph. You have 1, 2, 3, 4, 5, and you create another set, let us say 1 prime, 2 prime, 3 prime, 4 prime, 5 prime. If I follows j, you will draw a line from I to j prime. 1 follows 2, so you will follow a line from 1 to 2. 1 follows 3, so you will follow a line from 1 to 3 prime. So, 1 follows 2 and 3, so there will be a line from 1 to 3 prime and 1 to 2 prime in this graph. 2 follows only 5, so there will be a line from 2 to 5 prime, and there is no direction in this. This is like the purpose of duplicating the vertices is to 1, 2, 3, 4, 5 are the kind of the source or the follower version of the nodes, and 1 prime, 2 prime, 3 prime, 4 prime, 5 prime are the followed version of the same nodes, same profiles. So, 2 only follows 5. So, here is a line from 2 to 5 prime. 3 does not follow anyone. So, there is nothing out of 3. 1 follows 3 prime is there. 4 does not follow anyone. There is nothing out of 4. 5 follows 3. So, there is a line from 5 to 3 prime. This is bipartite graph representing So, this network N can be represented by this bipartite graph. There are many other applications of bipartite graph, namely you are actually you may be interested in flights from one flights between two different countries. So, you take India and US, you are just interested in which cities of India are directly connected to which cities of US, or which, let us say you are interested in two continents, you may be interested in which capitals of Asia are directly connected to which cities of Europe by direct flight. That is also can be an example of bipartite graph. There are many other examples in many other applications. So, a tree is a graph where there is no cycle. So, basically a tree is a graph where a graph is what? A bunch of things like this. A tree is like, if you start with one point, you keep going via edges, you never come back to a point which has already been traversed. This is not allowed. So, this will be a tree. This is not a tree. This is not a tree. So, anything which has a cycle there is not a tree. So, another way of saying that there is a unique chain of edges that leads from one vertex to another vertex. For any two vertices, it is first of all connected graph, that is 2 points are connected via chain of edges and between any two edges, any two vertices, there is a unique path consisting of edges leading from one to another. That is an equivalent way of saying there is no cycle structure. By the way, I will give a reference of basic graph theory books in the my reference for today's class. I will give a reference for basic graph theory. You can read all of these definitions and some of the ramifications. It will be good to read some basic graph theory along with what I am doing here to get a better intuitive grasp of random graphs. I am not assuming any graph theory, unlike linear algebra and probability, which I kind of assume that some familiarity. Graph theory, I am not assuming anything, whatever I need I am defining, and theory of graph theory will not be, theoretical aspect of graph theory will not really be needed, but nevertheless more, I mean anyway, more you study it is better for your understanding, and because of the inherent nature of network data, if you do some reading of graph theory, maybe few chapters of a textbook, it will give you a better grasp of what you are dealing with. So, a complete graph is a special case of graph where any pair of vertices are connected. So, you have but n vertices, if any two are connected to each other, then it is called complete graph. So, there are n vertices, then potentially n choose 2 edges, all are there. So, this is a basically a clique in a graph is a subset of vertices whose induced subgraph is complete, that is the graph on those vertices is complete. So, this is a example of a 3 clique, that is a complete graph on 3 vertices. So, this is another example of complete graph on 4 vertices. So, if you have 5 vertices for example, what will be a complete graph? These two will be connected. This is so number 1, number 2, number 3, number 4, number 5. Any pair is connected. So, 1 2 is connected, 1 3 is connected, 1 4 is connected, 1 5 is connected, 2 3 is connected, 2 4 is connected, 2 5 is connected, 3 4 is connected, 3 5 is connected, 4 5 is connected. Every pair will be connected. And remember, like we are defining, so for our purpose we are only defining what is called simple undirected graph. So, you have bunch of vertices. Edge means edge between two different vertices, and two different vertices are either connected by an edge or they are not connected. In application, if we need some variation, we will define them. Maybe we will use bipartite graph, we will use weighted version. For now, we are defining the most basic thing, which is simple undirected graph. No vertex can be connected to itself, and two vertices are either connected by an edge or not connected. So, that is it, and no direction. Directions, of course, we have seen can be taken care of using bipartite graphs, just but that is not, and for multiple, if there are need for multiple edges, sometimes putting in weight on the edge will take care of that too. So, two graphs are called isomorphic if there is a bijection between vertices such that if UV is an edge, and then two graphs are called isomorphic if there is a bijection between vertices such that if UV is an edge in E, then phi u phi v is an edge in E prime. Basically, graphs have identical structures up to releveling. Just to give you an example, if you have this pentagon, so 1 2 3 4 5, and you have this star. These two are actually isomorphic. Why? If you take this 1-1 correspondence where you send 1 to 1, let me just do it with primes. Take 1 to 1 prime, 2 to 4 prime, 5 to 2 prime, 4 to 3 prime, and what is left is obvious, 3 has to go to 5 prime. So, what does this do? You take 1 prime to 4 prime, equivalent to 1 going to 2. 1 prime to 4 prime is connected, 1 to 2 is connected. Then here it goes 2 to 5, here you go from 4 prime to 2 prime. Then you go from 5 to 4 here, here you go from 2 prime to 3 prime, and finally you go from 4 to 3, here you go from, you can see you can go from 3 prime to 5 prime, and 4 to 1 you go from 5 prime to 1 prime. So, same structure is being repeated here as here. So, this is called graph. This is called graph isomorphism between graphs. So, a cycle, as we just saying, like we use this word cycle. A cycle is basically a connected graph such that on n vertices such that v1 v2 is an edge, v2 v3 is an edge, vn minus 1 vn is an edge, and finally vn v1 is an edge. This is called a cycle C4. A degree of a vertex is denoted degree v is the number of edges that are incident to v. One can check that degree of a vertex v is just 2 times the number of edges, and this is basically gives you an example of that. And we define this in first module itself. For graph on n vertices, the adjacency matrix is defined by 1 in the position aij on the ijth position if ij are connected, and 0 otherwise. So, basically there will be all zeros in the diagonal because no vertex is connected to each other, and it will be symmetric because ij connected and ji connected is basically considered same. So, for a path 1 to 3, you see that 1 2 is connected. So, there are 1s in 1 2 and 2 1 position, and 2 3 is are connected. So, both 2 3 position and 3 2 position there are 1s and zeros everywhere else. A random graph, now we are getting into the domain where which is relevant extremely to our social network analysis. Random graph is a probability distribution on a set of graphs. So, you have bunch of graphs, it may be finite, it may be infinite, does not matter, G1, G2 dot dot dot. Basically, if you have a class G alpha, alpha belongs to some A set and G alpha graph for all alpha. A random graph model is a probability distribution on this set, that is, you can choose various graphs with various probabilities. So, for example, a simple random graph model can be this triangle probability 1/3, 1/3, 1/3. So, suppose you know that 3 nodes, 3 profiles, 3 people have 3 potential relation structure, either all are related to each other. So, you know that them 1, 2, 3, either 1, 2, 3 all will be related to each other, or 2, 3 will be related, or 1, 2 will be related to each other, or 1, 2, 3 each will be separate, there will be no relation. Suppose these are the 3 possibilities, let us say you know somehow, and each has probability 1/3. So when you are making a draw, just like you toss a coin, you get head and tail. Here you will pick from one of these three with probability 1/3. So taking value, you remember for Bernoulli distribution, random variable takes value 1 with probability p, 0 with probability 1 minus p. Here your random variable takes this graph as a value with probability 1/3, this graph as a value probability 1/3, this graph as a probability with probability 1/3. So this is called random graph. So where your random, now we are getting back to our formal language of probability distribution. Probability distribution basically is of a random variable which takes various values as various graphs. So the random variable x takes values g1, g2, g3 with various probabilities, and each of these values are graphs, the way we have defined. That is called a random graph. So this is our most important random graph model, which is called the Erdos-Renyi random graph model. So this is basically probability distribution on graphs with n vertices. So the two classical versions for random graphs that people take, each edge is included independently with probability p, where p depends on n, and another one is that you take all vertices with all graphs with exactly m edges with equal probability. So we typically focus on the first one for this. I mean, that's probably the most, that's actually the most important random graph model in literature, and well, if not the most, let's say one of the most important models, and we'll focus on this GNP random graph model, where you have n nodes. One, so your random variable x, which takes graphs as values, one value of x, one iteration of x, just like for random vectors, essentially consists of, you know, a vector value, like a value of a random vector is just a tuple of values. Here value of a graph valued random vector or a random graph is essentially a graph. So how do you get that graph? So the probability of getting a particular graph is just tossing a coin for each edge. If you get head, you have that head. If you get tail, you don't have that edge. So to explain this, so vertex set is fixed 1 to n. Each of n choose 2 possible edges are independently selected. Whether edge ij is there is independent of edge I prime j prime is there or not. So basically you toss a coin with probability p for every edge, that is, you toss a coin n choose 2 times. For whichever edge you get head, you join that edge. Whichever edge you get tail, you do not join that head, that edge. You do it for all n choose 2. The end product is a graph. This whole combination of n choose 2 independent tosses together and then joining the lines wherever there is an head, leaving out the lines where there is no head. This whole process that gives you a graph on n vertices as a final result is one observation of your random variable. So graph valued random variable gets this one particular graph as a value, and the probability of course, if there are m edges, and because they are all independent, all the edges all the tosses you are doing independently, any graph with small m number of edges will have probability p to the power m times 1 minus p to the power n choose 2 minus m, because this is essentially at the toss level n minus 2 independent Bernoulli trials. So the probability of the totality will just be the probability of each of them multiplied together. So expected number of edges for a random graph will be what? So what will be expected number of edges? So expected, what will be the expected number of edges? So you can, you know, there are, it's up to n choose 2. So the number of edges can take values up to n choose 2. So the probability of this being m is n choose 2, that is the total number of edges. Out of them m are there, and choose m times p to the power m 1 minus p to the power n choose 2 minus m. When you are concentrating on number of edges, this essentially becomes an expected value of a binomial distribution. So, number of edges basically follows binomial total number of trial n choose 2 with probability p, and you know for binomial NP, binomial Kp has expected value Kp. So, the answer is p times n choose 2. So, if you start with a Erdos-Renyi random graph, the probability of getting a particular graph as an outcome, as an one observation, is p to the power m 1 minus p to the power n choose 2 minus m. The expected value of the expected number of edges there will be p times n choose 2, because it follows a binomial distribution. So, various other things, other nice properties follow from the known behavior of binomial distribution for Erdos-Renyi random graphs, and that leads us to various asymptotic, nice asymptotic behaviors, which will be concern of our discussion, our subsequent discussions. I have put some of it in the notes. So, for example, this is a small example of Erdos-Renyi random graph. You basically you have 4 vertices, and so 4 choose to 6 possible edges, each appears with probability p. So, if you take for example a complete graph, the probability of that is actually going to be p to the power 6. So, the probability of this will be p to the power 6, because all of them are appearing, because 6 possible cases you are tossing 6 possible edges independently, you are tossing a coin. Here the picture shows that you have got all possible pairs. So, basically p times 6, so p to the power 6. So, some typical structures, and these are going to be common occurrences we will see. If p is some c over n, we call it a sparse regime, because as n goes to infinity. So, generally speaking, for random graphs, what we will see that the p depends on one recurring theme in the random graph will be p depends on n, the number of vertices. So, p generally is fn, the function of n. If generally p has n in the denominator, as n goes to infinity, let us say some constant c over n, as n goes to infinity, p becomes smaller and smaller, that is called sparse regime. And if as n goes to infinity, p actually behaves like a constant, remains constant, it is called a dense regime. So, various different regimes will have various asymptotic behaviors that we will see in actually I will start from these asymptotic behaviors in our next class. Thank you very much. I stop here.